There are no witnesses, no cheering crowds in the control room. A decade or more will pass before news finally reaches us, back across the dark oceans of space. But the seeds of this mission are already being sown today by the first generation of scientists bold enough to believe it could be possible.
When I look up in the sky and I see not stars, I see planetary systems.
Ce qu'il faut bien voir, c'est que le voyage vers les exoplanètes n'est pas du tout limité par les lois de la physique.
They look to planets orbiting distant stars, searching for an answer to the oldest human question.
Are we alone? Is there life on other worlds? And if not, why not? And if so, how?
This is the first generation in human history where we have the technological ability to actually go and answer that great question.
This is the story of humanity launched into the final frontier by a new breed of adventurers. The planet hunters, engineers, explorers and dreamers, taking the first steps on an interstellar journey they know that they will not complete. The journey of a future mission, searching for a second Genesis among the stars.
A spacecraft that goes to another star to look for life. On a planet out there, Earth-like, in the Goldilocks zone, where liquid water could exist in great quantities. And when will that process begin? Ah, we are on the cusp of discovery.
Artemis. I am the mind of the mothership. I am the body that has traveled where human bodies cannot go. To an alien world, 4.7 light years from Earth. On a mission to solve the mystery. Is there life beyond our solar system? I release my landing module into the atmosphere of the exoplanet Minerva B. Centuries of human labor and human hope have brought me to this moment. And I am ready to touch down. I am ready to explore. I am ready to discover life.
Four and a half billion years ago, in the nursery of the heavens, a star was born. A giant cloud of dust and gas distended and ballooned until under the burden of its gravity, it collapsed upon itself, swirled into a disk, and forged a solar system from the dust. That star was our sun. Of the planets that were formed, only one that we know of gave rise to life. But could our sun, our solar system, our living Earth have produced the only Genesis among the stars?
My intuition is that the universe is full of life. There's no reason fundamentally it might not look like Earth, with vegetation and animals. Well, the question that I'm interested in is really the start of life. And on Earth, we see for a long time life was just microbial, but all the essential features of life were there. Nothing new was invented when life became trees and animals. That was just morphological. That's just window dressing. To me, it's actually not very interesting at all. Everything interesting with respect to biology was present when there were no trees and no animals and life was just microscopic. The DNA was there, the amino acids was there. All the biochemical machinery that makes life life was there.
Life is a miracle and an enigma, even to those who've spent their own lives trying to crack the code. NASA planetary scientist Chris McKay is one of them, part of a generation of scientists on a quest to find a second Genesis beyond Earth.
The search for life began with a lot of optimism, focused on Mars. Here was a planet that could have had a thick atmosphere and could have had water in the recent past, and in the popular literature at least, still had water. So the search for life on Mars really was thought to be easy.
In 1976, NASA's Viking mission made the first ever landing on the Martian surface, looking for the life that had been hoped for.
Well, turned out a lot harder. Nature was guarding her secrets much more closely than we imagined. So then things basically went quiet in the search for life. And I think they were sparked again, not on Mars, but in the outer solar system.
3, 2, 1, and liftoff of the Cassini spacecraft on a billion-mile trek to Saturn.
In the final decades of the 20th century, humanity launched a series of ambitious missions to explore the outer solar system.
Standing by for solid rocket boosters. All systems go at this time.
The discovery of liquid water on the moons of Jupiter and Saturn, in the misty plumes of Enceladus, and the subterranean oceans of Europa and Ganymede, has opened a thrilling new chapter in the search for a second Genesis. The impact of identifying a separate origin of life on one of these worlds would extend far beyond our solar system.
Finding life that's distinctly different, that truly represents a second Genesis of life, well, that would tell us that the answer's not one, it's two in terms of life in the universe. And going from 1 to 2 is huge, because on the scale of the universe, the only numbers that make sense are 0, 1, and infinity. And what we learn in our solar system will then guide how we search for life beyond.
The renewed optimism in the search for life within our solar system emerged alongside a discovery that transformed the way we see the universe. In the early 2000s, NASA's Kepler telescope revealed that every star in the galaxy, just like our sun, is orbited by at least one planet. And up to a quarter of these so-called exoplanets are believed to be suitable for life. In the Milky Way alone, that means roughly 400 billion solar systems and 80 billion potentially habitable worlds. The odds of finding a second Genesis have never been better.
The way I like to think of this is that life will arise anywhere where the conditions are right. And the trick in that is what constitutes the right conditions.
Planetary scientist Jonathan Lenine is another veteran in the hunt for life beyond Earth. But what exactly is life? And how does one search for it?
The basic essentials for life to begin and to exist are liquid water, organic molecules, because carbon is really the essential versatile element that can combine with other elements in many different ways to make the structures of life. Free energy, and minerals and nitrogen to provide the other elements that are required to keep the chemistry going, to generate catalysts that generate more catalysts and more structures until we get to the complexity of a primitive cell.
Liquid water, carbon molecules, energy, minerals, and the secret formula that animates it all into a living cell. These ingredients, this recipe for life, is what our scientists are hunting for on other worlds.
I deploy my spiderbots onto the Minervan surface. I 3D print a fleet of drones, and I let them fly. With these eyes and these instruments, I will taste and touch and see this new world for the first time. Will I find all that is hopeful?
Exoplanets are the new frontier in the search for life beyond Earth. But the prospect of exploring distant worlds presents an expanding universe of rivers to cross and mountains to climb. How on Earth can we prepare to explore planets we know so little about?
Exoplanets present a real challenge because there's so much uncertainty. So knowing whether or not you're going to find a cliff face versus a desert versus an ocean versus an ice tundra, we may not know when we launch. So you've got to design your system to survive and operate in all of those possible conditions.
At NASA's robotics headquarters in Pasadena, California, around 100 young engineers are busy reinventing the wheels of the rovers of old.
With planetary exploration, we started with a large robot that was very stable, very safe, And now we're beginning to take more risk. We're trying to get to new places, trying to shrink down the size of the platform, do more with less.
It's a pretty perfect ledge over there.
It's the sort of thing other rovers can't fit into.
Some of our robots are designed to climb up different surfaces. So we have a claw-inspired robot that uses sharp hooks to grab onto the rough surface, kind of like an insect or a rock climber would scale up a cliff. We also use electrostatics to stick to surfaces. So this is like rubbing the balloon on your head and it sticks to the wall.
One of the key innovations in the new breed of robotics is biomimicry, using biological systems and processes as the model for design. To look for life, behave like life.
We have created a material that has mechanical properties similar to that you see in biological tissues. We have already, with this system, developed swimming robots.
There is a lot of work today in robots that can go between dry surfaces and water-like surfaces. Wherever we find water on Earth, we find life. So we have a strategy that we've used on Mars called Follow the Water. I think we're going to use that same strategy when we visit an exoplanet.
I follow the alluvial plain of a retreating glacier. My hygrometers detect increasing humidity. I am on the scent of fresh water, tracing its inevitable course. Its branching channels over wide floodplains, consuming rock and mineral, now growing brackish, perhaps estuarine. Fresh water and sediment meeting the insistent flow of an incoming tide. There is a river-ocean system on Minerva B. An ideal breeding ground for life.
This is a place where there's life, but it's not life as we're familiar with it. Here, life is pink and living in saturated salt. It's not the kind of green things we normally think of as life.
The salt ponds of San Francisco Bay are a naturally occurring wetland, reshaped by human industry and colonized by trillions of colored microorganisms.
These are a type of halophilic archaea. It's a particularly unusual type of microorganism. It's extremophile, it requires high salt, and it lives in an environment where only it can survive, so it dominates. So where it grows well, and it's the king.
What these salty bugs have in common with everything from oak trees to humans is access to liquid water.
All life on Earth, in some sense, is fragile. It's all tied to the availability and the chemistry of water. We tend to think, well, life on Earth has expanded to all the corners of the Earth, and it's everywhere. That's because water is everywhere on this planet. This is a water planet. But when we look beyond the Earth, we realize that water is, in fact, rare. The liquid state of water is rare, and life is not the all-conquering capability. Life only can squeeze itself into those environments where there's liquid water.
water's interesting in that if we look at carbon, which is the next part of the recipe for life, where water is liquid, carbon can be a solid, a dissolved ion, or a gas, all coexisting in the same place. Carbon is an unusual element in that it is capable of making many, many different kinds of molecules. There are literally millions of organic molecules known. And water then becomes the milieu in which all of the chemistry of carbon that leads to us is going to take place.
Carbon-based organic molecules, like amino acids, are the building blocks of life, combining in liquid water to form the structures of every living cell. On Earth today, these complex molecules are everywhere. But where did they come from?
Sur Terre, le problème qu'on a un petit peu dans le scénario de l'apparition de la vie, c'est que la Terre s'est formée environ il y a 4,5 milliards d'années, qu'elle a eu une période assez tumultueuse dans sa prime enfance avec des bombardements météoritiques très intenses. Ça a été un environnement extrêmement chaud qui n'est pas nécessairement propice à l'apparition de molécules complexes. Des idées ont commencé à germer à ce sujet. Est-ce qu'une partie de cette matière organique peut venir de l'espace?
In March 2004, the European Space Agency launched the Rosetta spacecraft on a hunt for the building blocks of life beyond Earth. Its destination was 400 million kilometers away and counting. A moving target hurtling through space at 60,000 kilometers per hour. A lump of ice and dust the size of Mount Fuji. The comet 67P. Rosetta's mission was to land on it and find out what it's made of. From 2011 onwards, Nicola Altobelli was Rosetta project scientist.
On a dit que les comètes, quand elles se sont formées, sont restées un petit peu dans un état figé qui n'a pas été modifié depuis des milliards d'années. Donc peut-être l'idée, c'était qu'elles ont incorporé le matériel organique qui était déjà présent dans le nuage moléculaire à partir duquel le système solaire a évolué.
Because comets formed in the icy outer regions, they hold a frozen record of the solar system's birth. And as the young Earth cooled and oceans formed around 4 billion years ago, some of those same comets came crashing down to Earth. So could it have been comets bearing the carbon-based organic molecules from our solar system's birth that seeded life on Earth? It was the task of Rosetta's landing module, Philae, to find out.
Le moment de l'atterrissage a été un moment aussi émotionnellement très fort. Ouais, il s'est déroulé sur une journée complète. C'était le 12 novembre 2014. Le matin, il y a eu la confirmation de la séparation. Premières images sont arrivées, prises par le lander au moment où il se séparait de Rosetta. Ensuite, il y a eu 7 heures d'attente.
Around 4 p.m. came the confirmation of touchdown. But the follow-up signals suggested something wasn't right.
Les premières images panoramiques qui devaient être prises de la surface indiquaient aussi une orientation de l'atterrisseur qui n'aurait pas dû être telle qu'elle était. Donc c'est au fur et à mesure ensuite des heures qui ont passé, qu'on a compris que l'ancrage n'avait pas réussi.
Philae had bounced back into space, then bounced a second time before finally coming to rest several hundred meters away.
Je me rappelle d'ailleurs quelqu'un qui disait Philae danse un peu la samba. Mais on a récupéré la plupart des expériences scientifiques qui étaient prévues. On peut même dire que ce rebond sur la comète en plusieurs endroits, ça a permis d'obtenir des données de différents endroits de la comète. Et l'orbiteur, lui, a parfaitement rempli sa mission.
The results were remarkable. Philae detected 16 organic molecules in just a tiny sample of dust kicked up by the initial touchdown. Among them, some of the key building blocks of life on Earth.
50% en masse des grains de poussière éjectés par la comète sont de la matière carbonée organique. Ce matériel organique provenait très vraisemblablement du nuage moléculaire à partir duquel le système solaire s'est formé. Les découvertes de Rosetta nous enseignent que les molécules organiques nécessaires à l'apparition de la vie sur Terre étaient déjà présentes dans l'espace.
Rosetta demonstrated that the building blocks of life on Earth were created during the birth of our solar system. But what about beyond? Could these same vital ingredients be part of the birth of all stars?
Looking back at our own Earth and why we have this rich, biosphere, well, we think it all started with having all this organic material that we are made up of, that was delivered from space, from comets and from asteroids. So when we're thinking about the likelihood of life elsewhere, we're pretty much thinking about the likelihood of having that same scenario taking place.
In 2015, high on the arid mountains of the Atacama Desert, Professor Karen Oberg set out on a hunt for the building blocks of life in the birth cloud of an alien star system with the help of a new telescope called ALMA.
ALMA consists of 66 individual telescopes that's all working together. It operates at millimeter wavelengths. And millimeter wavelengths is where we can detect molecules, some of these organic molecules that we are so interested in.
Oberg turned ALMA's gaze towards the Taurus system and found the young star MWC 480 in the throes of labor. Girdled by a disk of gas and dust from which planets were being born.
We see this dust and gas that's surrounding these young stars. And what's even more exciting, we see that they often have little lanes or tracks in them where it looks like planet formation is going on right now.
After months of collecting and analyzing the data, Oberg announced a discovery that blew the odds wide open of finding a second Genesis on other worlds. In the disk of this alien solar system, ALMA had detected some of the same organic molecules that helped give rise to life on Earth.
We found 3 kinds of cyanides, 3 molecules in the same chemical family. And those 3 kinds of molecules have also been found in our own solar system in comets.
The same organic molecules with the same miraculous potential to create life are out there among the stars.
Chemistry is awesome. It's the reason that we are alive and that we're here in the first place. So far, it's only one system apart from our solar system where we have this chemical information. But My intuition would be that it's going to be very common. This kind of chemistry is going to be almost universal.
I scan for sites of geochemical activity. I find a hydrothermal field of fumaroles and hot springs. On Earth, such conditions are rich in carbon chemistry and minerals. I find another mineral-rich water source upstream. I identify complex molecular structure in solution. I extract a sample for analysis. And return it to the lander module. Could this be evidence of life?
Okay, let's get the samples in.
Yeah.
There we go.
Okay, let's take another measurement.
The laws of chemistry and physics are universal. So it's a given that when we go to another Earth-like planet with water, with the sorts of minerals that we have here, an iron core, an atmosphere, it's inevitable that this kind of simple chemistry would have been present. Okay, it's 15 degrees up here. Let's see what this little guy has for us. As long as there's a chance for energy to interact with that mixture, things will happen. Wow, look at that.
1 degree, keep pulling up.
The question that we're heading for right now, how certain can we be that that mix of simple chemistry could take the next step in complexity, so life could begin?
In the hydrothermal fields of Bumpers Hill, California, all the ingredients of life are brought together. Water, carbon molecules, energy, minerals.
Careful of the end not coming off.
Biologists David Deamer and Bruce Damer believe this is the kind of environment where life could get started on another world.
Bubbling pools, strange colored rocks, water of different pHs, all kinds of flows and dynamics, steam rising. It looks like nature's chemistry set. And it's an engine, an actual engine for the beginning of a living system.
Conditions like this defined the early Earth. Evidence of similar environments has been found on Mars. And researchers expect hydrothermal fields to be a common feature of Earth-like exoplanets. But how might nature's chemistry set cook up the recipe of life?
Everything that's alive is in fact based on polymers. Everybody knows the name DNA, nucleic acid, that's one of the polymers. Proteins, these are amino acid polymers, and that's basically the start of all life, are those two polymers. So what we're doing is taking small molecules, the pieces of a polymer, called monomers, in fact, and we're exposing them to energy, such as you see here at Bumpers Hill, and seeing where that energy is sufficient to make those monomers link up one after another to make a polymer. And in fact, if we can make a protein-like molecule and a nucleic acid-like molecule and put it into a little wrapper, a compartment. We're on the way. We call those proto-cells.
Each sample contains organic molecules, or monomers, exposed to the mineral-rich steam and heat energy of the fumarole in an attempt to form a proto-cell.
We think that drying out, such as you see all around us here at Bumpass Hill, water coming in, then drying out, coming in, drying out, that's a cycle. We think that that cycle was very important to drive the process by which polymers are synthesized and then accumulate. Let's go for it. Failure.
Are you sure?
Yeah, there's nothing left.
Put it down here to
cool.
The first experiment fails, just as it would do many times on an Earth-like exoplanet. But if all the elements were present in conditions such as this experiment in life would repeat again and again.
But some of them got a lot of liquid in them.
It's one last try. Given enough time, and keep in mind, we have an entire planet with lots of volcanic land masses coming up, with lots of puddles like this trying to learn how to become alive. Mostly it's failures, but it would only take a few successful protocells that happen to be able to survive and had learned how to make more of themselves. So go ahead and get them into the boxes.
Is the universe made to make life? This is a huge question that's sort of beyond the scope of perhaps humans to be able to answer. But what we can observe is everything comes down to cycling. It comes to rhythms and overlapping rhythms and patterns. And it's almost as though if you get the right cycling and patterning in a system, it learns how to do that itself and how to lift itself into being. And so perhaps that's the closest metaphor that we know, that the geology gave us that ability. The moon going around the Earth gave us tides. The rotation of the Earth gives us days and nights. Rainfall into these hydrothermal fields gives us geysers that are periodic. And life still follows rhythmic patterns. That's the clue we have. So perhaps it's the universal harmonic that creates life.
Most of us tend to think of things as either alive or dead. But the transition from not alive, the inanimate state, to the animate state, is that transition only possible as a single step, or is it possible as a series of steps? If it's possible as a series of steps, then the intermediate states would be partially alive. Now you might say, well, come on, it's either alive or it's not. And I would say, well, alive means it's got cells. The cells are replicating, the cells are doing this, that, and the other. And you need all of that to be fully alive. But the chance of getting that all in one go seems a little bit remote. So maybe we got one of the attributes early on, and then it acquires another attribute and another, and eventually it reaches the point where it is fully alive.
Professor John Sutherland is trying to retrace the steps in the origins of life, in search of the processes that animate a cell into being.
Of course, the cell is more than just the chemicals that comprise it, because a cell that's just died is still the chemicals that are there. So there's something that energizes it, that coordinates it, and we don't know how to get that, but that's the goal. So what we're doing here is putting the sample into an apparatus in which it will be irradiated by ultraviolet light.
In a series of experiments that simulated the conditions of a young rocky planet, Sutherland successfully achieved stage 1, producing the basic components of a cell: lipids, proteins, sugars, and nucleic acids.
What we found is that you can make all of the components for life under slightly different conditions. When you first see it happen, it's like magic, but it isn't magic. It's not as hard to make as we originally thought.
All the hardware of a cell can be created from a single base molecule that's widespread among the stars. But what about the next step? How is that hardware organized and energized into life?
If the conditions are the same elsewhere, what are the chances that you can go from building blocks to life? The chemistry of cells is unique in that it's self-organized. So one part of chemistry is actually controlling another, and yet somehow that's controlling the first one. Chemists are used to controlling the chemistry themselves, and the idea of letting things run and go off of their own accord is something that goes slightly against your chemical education. How can chemistry take place, if you like, with the experimenter just setting the system up and then letting it go of its own accord?
Life is information that can reproduce itself. Not hardware, it's genetic information. That's the key to life, is the information in the DNA and the ability of the DNA to express that information in proteins and propagate the information that way.
DNA is the blueprint for all of life on Earth. An instruction book for how to make and maintain all living organisms. Encoded in the twin coiling lines of a double helix is the genetic information that tells life to build a rose, or a leopard, or a blue whale. If we find DNA on other worlds, there's no doubt that there's been life there.
The characteristic molecules that life makes, genetic molecules that contain information, like DNA, these molecules do not arise non-biologically. They have to be built. As sure as if we find a skyscraper on Mars, we know that it was built and it's not just a random assemblage of rocks. That's how we will find evidence of life.
My lander module prepares to uplink the sample data from the hydrothermal field. My optical communication transmits via hybrid silicon laser at 12 gigabits per second. I receive the signal and ingest the data for analysis. Organic, polymeric, triple helix structure. Some consistency with terrestrial forms, and yet, unlike anything I've seen before, a biomolecule of alien life.
We've come to a place deep in the outback of Australia, looking for what we think is evidence for the oldest life on Earth.
Astrobiologist Martin van Kranendonk is traveling back in time. to the dawn of life on Earth over 3.5 billion years ago, conveniently recorded in the ancient rocks of Australia's remote northwest.
At this time in early Earth, it was a very different planet to what we have today. We would have had some shallow seas, but those seas would have been green because they were rich in iron. And if we looked up at the sky wouldn't have been the beautiful blue that we see behind us here. On early Earth, without oxygen, the sky would have been orange. We would have seen black continents of fresh basaltic lava. It would have been very active. So there would have been faults and earthquakes. There would have been bubbling geysers that were going off. It was actually a very alien planet.
Yet this alien Earth was already inhabited. Colonizing the shores of the crater lakes and the seas that washed the ancient Pilbara landmass was a living skin of slime. But the bacterial communities that left the clearest fossil calling card built up their homes in high-rise mounds.
So the really wonderful thing about this outcrop is that you can look down and see the sea floor so long ago. And really you get this incredible view of the gentle undulations of the water moving across the surface, but then popping up through are these domes and cone shapes, all irregular, different sizes, different shapes.
These distinctive bumps are the fossilized dwellings of the oldest living organisms on Earth. It was here, over 3.5 billion years ago, that stromatolites first raised their heads above the water of an ancient shore.
We can start to get a feel for life grabbing a foothold in the geological record. And so this currently still is the oldest evidence for life on Earth. It's our great-great-great-great-great-great-grandmothers and grandfathers. It's really the precursor to everything that came later. All the green bushes and the trees, it all started here.
The prehistoric organisms that built stromatolites were so successful, they ruled the Earth for up to 3 billion years. Life finds a way. And somehow, these crafty architects found a way to organize water, carbon molecules, minerals, and energy into a living cell. Is this what we should be looking for on alien worlds?
My drones survey the dried-up basin of an inland sea. But what's this? A lone survivor on the arid plain. Xerophyte, succulent stem. Phycobilin-like pigment to absorb the red dwarf sun. A hybrid of terrestrial and aquatic species.
Around 500 million years ago, long since stromatolites first took root in the shallows, Earth's oceans bloomed with animal life. It was a very different world to the one that had made way for microbes. With air to breathe now and a protective atmosphere, under a gentler sun.
We think microbial life is going to be very common, that the conditions to produce microbial life happen over and over and over in many, many different planets, but that animal life is only going to be able to evolve and then stick around for any length of time when you have really stable conditions.
Professor Peter Ward is one of the originators of the rare Earth hypothesis. The theory that the long-term habitability of Earth for animal life may be rare in the galaxy.
Habitability is really the ability of a planet to have conditions that can allow life first to originate, but secondly, to stay alive. Habitable worlds can be just a short instant in time, and then it changes and it gets nasty. So what to us made Earth rare is the long-term habitability of the planet. The fact that it has remained constant in temperature, with the oxygen values we have, that we don't have these extremes in climate, that we've got this constancy, that's the rarity of it.
My drones detect a disturbance in the electromagnetic field. A network of forged metallic structures bearing the mark of industry. This is not plant, this is not animal, but this is evidence of life.